Hello. So I'm going to talk about Python bindings for the Decompiler, which I wrote a couple months ago. All right. All right, so I don't see anything actually. I'm going to switch the... Wow, okay. My name is Francois Chagnon. I'm a student here in Montreal. I'm studying software engineering. It's my third REcon. I'm a volunteer and also first-time speaker. I like security. I like reverse engineering, and I'm almost done with school in a couple of months. So there's a great API for the HexRays Decompiler, but writing C code is slow. Writing Python code is faster, so now we can do it in Python. You can use the API for the Decompiler. You can grab it here. The username is not case sensitive, so just go on GitHub /Einstein, and that's a minus sign because GitHub already has another Einstein. Yeah, the bindings are basically everything that's inside the hexrays.hpp file. You can find every function, every structure, everything from there. You can use them in Python. There's swig wrappers, just like IDA Python, and is a little bit more Pythonic. So you can, for example, list structures. You don't have to use iterators. You can index them directly. Everything is wrapped for you, and it's easier than writing the C version. Lots of times it's faster. So this is what it looks like. You just import the module, and you go hexrays.decompile. You pass it the address, and then you can print or do whatever you want with it. Here I have an example of getting the variables. That's very easy. You get a list. Just a small example. So like the talk this morning presented, actually they presented way better than I'm going to. But you have two structures. You have statements and expressions. So statements are, for example, the returns, the if, the while, etc. And they contain expressions, and expressions also contain more expressions. So you have like this kind of nested tree of objects that you can explore. And if you're familiar with the lexers, parsers, they're very similar. You get almost the same type of objects, same type of data to work with. So this is what it looks like. For example, you have the if statement, and then you have a lower than expression, an identifier, and then a minus expression, which contains numbers, and also another identifier. So very easy to iterate and work with. So first example. So I thought about what could I present that would be useful to some of you, and I'm tired of the old xref. So when you're working with the disassembler, you get this type of xref, and when you're working with the decompiler, you're working with pseudocode. So when you want to see the xref for a function call, for example, you get this type of window, and you don't see the parameters, you don't see anything. So I wrote, I'm going to have to exit this mode. All right, and now I don't see anything. So first demo. I hope you can see this. So you have like a small example. When you click on X, you get this. It's not very useful. You see that it's called every time. You don't see any parameter. So let's load this. And now, when you click on X, it decompiles every function in the program, and you see the parameter. You see everything. It's much better. And you can click on them, and you see where it's called. So that's a small plugin. It's about 200 lines of Python. It's very simple. And I think it would have taken much more time and lines of code to do this in C. It's also easier to modify, obviously. So let's go back to the presentation. So let's look a bit at the code. It's very simple, as I said. There's 200 lines, but there's very little actual use of the API. So I'm going to present the big lines of this. So you install a callback, and every time something happens in the decompiler, you get you get a function executed, and you can see what's happening. So you get many GUI events. You also get the maturity changes. So every time the function is transformed by the decompiler, you get a callback. So in this case, we want key presses. Also, the right click has a link to show the xref. So step 2, you figure out what item the cursor is on. So you can have the function prototype, which is the first line of the program, the variable, which are the following lines, or any expression in the body of the program. So here we're interested in objects, so functions, integers, or strings. They all work. So whenever we have that, we get the xrefs for those and decompile the function, and then we get the statements that address end up in. So the EAMap is a translation between the address and the statements that it gets combined in. So another example, and then so my second example is actually, so I made a fake program which encrypts strings. So like you see this in malware all the time. So this is a decode function. So you have like a simple decode function, but this could be much more complex, of course. So this small little program basically takes the C syntax, and instead of displaying it in C, it prints Python. So you can like re-execute the same function in the interpreter directly. So let's see here. Okay, so let's get in the function, and then we call pyprint, and it prints the function, the C tree, as Python. I hope you can see this. Okay. So after that, you can just like execute the displayed text, and then it gets added to the interpreter context. So now I have like a decode function here, and this is without any effort. So this function is very simple, but there could be a more complex code that you want to translate, and this happens all the time. So by doing it automatically with the HexRays API, it's much simpler. So afterwards, you can execute it directly. So since I can't see what I'm doing here, okay, so this is the first line in the main that I copied. And the thing is, in Python, strings are immutable, so I simply wrap the string in a byte array, and then I can modify it. So when I execute this, the function gets executed, decode function, and the text is displayed. So I can combine this now with the xref that I showed earlier, and then I can just copy this line. Actually, Control-C works in this plugin. So just copy this line and paste it, and same stuff. You can decode it, and you see like v1 now has the variable, the decoded string. So that's two simple scripts. They're both under 300 lines of code, just to show you how to use the API, how simple it is. So all right, so I have another project that I'm going to present. I thought, I don't think there's any talk ever at REcon that talked about decompilation. I could be wrong, but anyway, a couple months ago, I also wrote my own decompiler just to see how hard it is. So I'm going to talk a little bit about that. So this is the project. You can go grab it now. It's a IDA Python script, so it doesn't use the HexRays part. So why do that? Well, HexRays is the HexRays Decompiler is a black box. You can't really see what's going on there, and I wanted to understand. So and it doesn't support 64-bit, so that sucks. If you do CTF, all of the hard challenges are 64-bit because they know there's no decompiler for 64-bit. So now I'm going to win faster at CTF. I wanted to see what's so difficult about it. HexRays Decompiler got out in 2007, I think, and there's still no 64-bit support. So what's so hard about like adding a few instructions, calling convention and stuff? So the basic is this. So you split up the function in basic blocks, just like think the IDA graph view. That's the same idea. And then transform the assembly in an intermediate form. Then from that form, you apply SSA form. You transform the intermediate into SSA form. And then you propagate a few expressions to simplify the control flow. And you arrange the block in a way that would tell something to like a programmer. So this is what it looks like. So you have the assembly and the intermediate form. So this is like add instructions. So you have the add, and below you have the same expression but in the intermediate form. So in the IR, all of the assignments are explicit. You don't have like implicit. You don't have anything implicit, and you can see that the add instruction was transformed into an addition. So that's and also the complex instructions are expanded into their alternate form, like in expressions. So you have a push here. That's actually an assignment on the stack, and adjusting the stack pointer. So you have everything that's expanded. So then you can apply SSA form. So the single static assignment is a form where every assignment only has one definition and a couple uses. So here you have, for example, EAX, and it's used here. When it's reassigned here, it has a new index, so it's considered a new variable. And then what you do is, static single assignment gets really complex, for example, with loops. So you see here there's EAX. It's used as part of the condition of a loop, and then it gets redefined. But since it's a loop, second time the condition is evaluated, there's a new EAX. So how do you index that? So is it all the same variable, or what is it? So if you want to know more about this, it's an interesting subject. Go Google these keywords, Van Emmerik SSA, and you can find the paper where this comes from, and he explains it much better than me. So after that, you can propagate expressions. So for example, you have the post increment, which is merged in the last statement, and then the registers, they're used only once, so they can be merged in the function call. And then you have like the original function call. So you do this for all of the blocks, and then you can combine the function flow. So here you have like a goto without an exit condition. So it's just a while, an infinite while. And so here's a couple of control flow that you can easily recognize. Like you have the basic if and if else. You have the couple of loops, and then you do that recursively, and you end up with like clean code that you can read as a programmer. So limitations right now, the project is on GitHub. It only supports like the systemv ABI. So registers, the function parameters are passed in EDI and ESI, etc. Doesn't support like STD call and everything, because I wanted to support 64-bit, and that's mostly what is used with 64-bit programs. It only supports, as I said, Intel. 32-bit and 64-bit is supported by the same plugin. Not every instruction is supported. I have like a limited subset, and it doesn't do type analysis. It only prints pseudocode, which doesn't have type information in it. But it's still pretty useful. Like it's faster than reading assembly, so it accomplishes its task. All right, let's see a demo. All right, third demo. So you have this here. It's a pretty basic function. Like it has a couple ifs. So you can use the decompiler here, and it gets printed out as text here. So this is a 64-bit function. It's as simple as that, and you can see that it's easier to read than the original assembly. There's also a graph mode right here. So you get, put it here actually. So you get like the same view as a graph view, but in pseudocode form. So I hope you can see this. So that's it for this plugin. Whoa. Thank you. Questions? No?
Have you looked into how to do type analysis?
Sorry?
Have you tried to do any type analysis?
Have I done type analysis? I haven't tried yet, because I'm only interested in something that's faster than reading assembly, and this, so far, it accomplishes the task in CTF and like for a limited use. So, yeah, I actually tried during last weekend at DEFCON CTF, but we didn't solve any challenges. But we reversed them quite faster than usual. So yes, question. Yes. Yeah. So I'm sorry, the XREF for can you repeat the question?
Yeah, so you had hyperparameter populated in the XREF.
Yeah.
How does that get updated as you continue to work on the binary?
Okay, so the printing of the actual statements is done by the HexRays Decompiler. So whenever you update your disassembly, your decompilation, actually, you just redo the xref, and the new like function call and everything is going to be updated. So, any more questions? Yes. So obviously, post increments and stuff like that don't exist in Python. So you might have to manually edit the Python code, but it should print something that is valid Python most of the time. Obviously, function calls are not the same, but for example, you have printf. You can replace that with a print in Python. The string operators are pretty much the same. So most of the time, it should work as is. Maybe the idea behind this is obviously you can automate it. So you can have like automatic replacement of function calls for something else in the Python API, and then you can just like disassemble stuff. If you have like a new version of some malware every week, you can like just disassemble and print to Python the same function that is in this malware, and then you get the new like decryption algorithm automatically in Python. So, yes, a question. Sorry? Yes. Well, there's nothing really hard about it. I think they just want to charge like $1,000 more for the next license in maybe a couple of years.
They already have the ARM one, right?
Yes, they have the
ARM and the x64 calling is actually almost the same.
Yeah, it's well, I don't know why they're not releasing it yet. I assume that they might have started work on it. I mean, it's really just a couple more instructions to support and different calling conventions, but the rest of the process is exactly the same. So, yeah, I know. This project is only a few thousand lines of Python. Maybe I'm at like 3,000 lines of Python right now, and it does like some stuff well, but it will probably break with like what you try to decompile. So yes, of course, this is not a product. That's why it's free too. So I think it's done for the questions.